Hi everybody. Okay, so we're going to use a regular, as you can see, Zoom now, since it looks like less than 300 people are coming. And the benefit of this is that you can ask questions just by speaking. So, if at any point I say, "Do you have any questions?" just unmute yourself and just ask the question. That's better for everybody than typing it. Certainly for me. So, okay. Good. However, please restrict the chat to actually things related to the lecture, because otherwise I keep getting notifications. Yeah. So it's lecture 7. And I guess I might as well use this glove. And just to recall, so last time we did 3 things. So we talked about one-to-one and onto linear transformations. And then we talked about this new kind of operation on linear transformations, which didn't exist before when we were only talking about equations and matrices, which was a composition and inverse of linear transformation. So composition, remember, was literally if you have 2 transformations, TA and TB, then TA of TB, is just defined as TA applied to TB. And one thing to keep in mind here is that you write TA of TB, but first you apply B, then you apply A. Which makes sense when you write it this way. And then we also define the inverse of a square transformation. So if T is going from Rn to Rn, then it's invertible if it's one-to-one and onto, and the inverse has the property that it undoes the action of T. So T inverse of T equals identity, which is also equal to T of T inverse. And this only applies to square transformations. And then finally, we talked about matrix algebra. So we talked about multiplication and inversion of matrices. Actually, just multiplication. We didn't get to finish. And the key property of matrix multiplication that I want to emphasize, which really the meaning of matrix multiplication, is it corresponds to composition of linear transformations. So if okay, so the product A times B corresponds to, or AB is the standard matrix of the composition TA of TB. So that's what we did last time. And this time we're going to do 3 things also. So first, I'm going to talk about the inverse of a matrix. This is a very central concept in this course, as you'll see from the types of theorems we prove about it. So first, I'll tell you what it is, then I'll tell you about how to compute the inverse. And then finally, I'll introduce a new operation on matrices, which is very important, called the determinant, which is closely related to the inverse. And we'll be mostly using it after the midterm, but I'll just go over it now. Okay, so let's get started. So what's the inverse? So here's the definition. So the inverse is only defined for a square matrix. So a square matrix A, let's say it's n by n, is invertible if there's some other matrix, if there's an n by n matrix C such that A times C is equal to C times A is equal to identity. Okay. So again, remember, identity is this very important matrix which just has as its columns it looks like this, and it corresponds to doing nothing, right? Identity times x equals x. So that's an invertible matrix, and then if there is such a matrix C, that's called the inverse. So such a C, if it exists, is unique and called the inverse of A, and it's denoted A inverse. So okay, so algebraically, this looks kind of similar to what we mean when we talk about the inverse of a number. So the inverse of 3 is 1 by 3, right? That's a number because 3 times 1 by 3 is 1. So this, multiplying by 1/3 undoes the action of multiplying by 3. So this is the analogous concept for a matrix. Multiplying by C undoes the action of multiplying by A. A times C is equal to identity. So one remark is that in this definition, it's actually enough to just check that A times C is equal to identity. That implies that C times A has to be equal as well. So that implies C times A is equal to identity. We won't prove this now. You'll see a proof of it later. But now let's get to what this means in terms of linear transformations. So the most important meaning is in terms of linear transformation. So meaning number 1, which is in terms of linear transformations. And the meaning here is that so if A is n by n, if A n by n is invertible, then A inverse is the standard matrix of the inverse linear transformation of multiplication by A. Is the standard matrix of TA inverse. That's a linear transformation from Rn to Rn. Okay, so this is the inverse as a linear transformation of TA. Okay. Now, this may look a little abstract. Let me just give you, well, first let me give you a proof of this. Well, the proof is that, let's look at multiplication by A inverse applied to multiplication, composed with multiplication by A, applied to some vector X, right? So for every vector X in Rn, or maybe let's not use a colon since we've used it to mean something else. What is this, right? So, well, TA inverse, that's multiplication by A inverse, that's just A inverse. TA is just multiplication by A, that's just A times X, right? So the T of A inverse times TA, composed with TA of X is A inverse times AX. That's A inverse AX. But look at the definition, A inverse A is the identity. So this is X, right? And also, if you do it the other way, if you look at TA of TA inverse of X, then that's A times A inverse times X. which is identity times X, which is also X. And that's it, right? So the conclusion is that multiplication by A inverse is the inverse transformation of multiplication by A. But then that means that A inverse is the standard matrix of the inverse of TA as a linear transformation. So the proof is very straightforward. Maybe the conceptually challenging aspect of it is that we're thinking of two different kinds of inverse, right? You have the inverse of a linear transformation. So this is the inverse linear transformation, and this is the inverse matrix, right? At least this part here is the inverse matrix. So the content of this is that that indeed this algebraic notion of matrix inversion corresponds to the sort of conceptual operation of inverting a linear transformation. So maybe this has become more clear with an example. Let's do an example. Well, let's take t to be the rotation by pi by 6. So what is that? Well, okay, sorry. So that's a linear transformation. It's not a matrix from R2 to R2. So what is its matrix? Well, it has standard matrix A, which is this, right? Cosine pi over 6, sine pi over 6, minus sine pi over 6, cosine pi over 6. We worked that out a few lectures ago. And now what's the inverse transformation? Well, that's rotation by minus pi over 6, right? Right. So by inverse transformation, I mean that this satisfies t minus pi over 6 of t pi over 6 is identity. Well, what's its matrix? So its standard matrix, let's call it C for now, because we don't know it's the inverse yet, is cosine minus pi over 6, sine minus pi over 6, minus sine minus pi over 6, cosine minus pi over 6. And now, okay, by trigonometry, this is just cosine pi over 6. Well, I mean, okay, let's just be very concrete here. We know what these are, right? So the first matrix, cosine pi over 6 is square root 3 over 2. Sine pi over 6 is a half. And now we know we can do the same for this. So cosine minus pi over 6 is square root 3 over 2. Minus sine minus pi over 6 is a half. Sine minus pi over 6 is a minus half. And this is square root 3 over 2. And if the theorem is true, then these should be inverse of each other, right? And let's check. Indeed, A times C is, so now we have to multiply these two matrices, right? And we know how to do that. So the first entry is going to be 3/4 plus 1/4. Second entry is, let's see, square root 3 over 4 minus square root 3 over 4. Then the bottom left entry is going to be square root 3 over 4 minus square root 3 over 4. And the last entry is going to be, let's see, have I got it right? Yeah, 1/4 plus 3/4, which is indeed the identity. Okay. So that's the content of the theorem, that this algebraic operation of inverting a matrix corresponds to inverting a linear transformation. Any questions? Okay, so that's meaning number one. Let me now get to meaning number two. There are many meanings of the inverse, but the second one I want to emphasize is related to linear systems. Okay, so let's assume you have an invertible matrix with an inverse, right? So assume A is invertible and it has some inverse with inverse A inverse, right? Let's assume it's n by n. Only square matrices can be invertible. Now, what does this say about linear systems? So let's write down a linear system, right? So AX equals B. So that's a linear system, right? X is a variable. Well, this is true if and only if A inverse AX equals A inverse B. Why is it if and only if? Well, I can take an equation of vectors and multiply both sides by a matrix and it'll still be true. So this direction is kind of obvious. Why is this direction true? Anybody know why? Why does the second equation imply the first equation? Please speak, if possible.
They're onto and one-to-one.
Well, these are matrices, so they can't really be onto or one-to-one, because maybe you mean the linear transformations, but there's a sort of easier reason.
Is it because the inverse of A is also a matrix?
Well, the inverse of A is a matrix, so that's true. That's important. So okay, let me write that. So to go forward, you just multiply both sides by A inverse, which is a matrix. That's fine. And to go backwards, how would you get from the second equation to the first equation? So, okay, some people have raised their hand.
Multiply both sides by A.
Yeah, just multiply both sides by A. So you're using that A inverse A is equal to identity and AA inverse is equal. I'm sorry, going backwards, you're using that AA inverse is equal to identity. Okay, but now the second equation, again, A inverse A is equal to identity. This is the same as X equals A inverse B. Okay. Now what does this tell us? Well, this tells us that AX equals B has a unique solution, right? A inverse is a fixed matrix. So therefore, AX equals B has exactly one solution for every B in Rn. Okay. So if a matrix is invertible, it says something very strong about the linear system, namely there's always a unique solution. So what's the summary? Or I mean, it's not a summary. In fact, you can prove, and we'll see this later in the lecture, that A is invertible if and only if AX equals B has exactly one. Maybe I shouldn't write equals one, just one, exactly one. Okay, I want to emphasize exactly one solution for all B in Rn. So we proved one direction, but the other direction is also true. We'll actually see the proof in a moment. So that's the other meaning of invertibility. And I should say that once you why does it have exactly one solution? So well, because of what's written here, right? I wrote the equation and I concluded that X has to be equal to A inverse B. It can't be equal to anything else. So there's only one solution. A inverse B is a fixed vector. That's a function of B. Okay. Okay, please ask questions by voice if possible. Okay. Okay, so this is actually the beginning of a massive theorem called the invertible matrix theorem, because this thing on the right-hand side, we've already seen it's equivalent to a bunch of stuff, right? So what's another condition for AX equals B has one solution for every B in Rn? That's the same thing as saying the row echelon form of A has n pivots, right? A pivot in every row, same as a pivot in every column. And you can continue this now because I'm actually going to combine pretty much all the theorems we proved in the course on one slide now, which is a good sort of summary of the big picture of the course. And this is something that in the book is called the invertible matrix theorem, but it's really like just a summary of all the theorems we've proved. So let me just write it down now. So here's the theorem. A is so let's assume A is an n by n matrix. And let's write down its columns, V1 through Vn, where these are now vectors in Rn. And let's assume it's the standard matrix of TA. Of T going from Rn to Rn. Well, let's just to emphasize TA. Right, so those are the three kinds of objects we've looked at: a matrix, its columns, there's a set of vectors, and a linear transformation, of which it's a standard matrix. Okay, so so then the following is true. So A is invertible if and only if the linear transformation TA going from Rn to Rn is invertible. And notice that these are two different notions of invertible, right? The first one is this notion where you talk about AC equals identity. The second one is one-to-one and onto. Okay. And why is that? Well, it's because of meaning number one, right? So if a linear transformation is invertible, or sorry, if a matrix is invertible, then A inverse is the standard matrix of the linear transformation. And therefore, the linear transformation is also invertible. Okay, but then this is equivalent to some conditions about vectors, right? So, or this is meaning number one. This is equivalent to a statement about linear systems. AX equals B has exactly one solution for every B in Rn. That was meaning number two, right? So let me just annotate these. This is meaning number one. This is meaning number two. But now, okay, now we can look back at, last week or the week before, right? This condition is equivalent to there being, this is equivalent to a certain statement about the columns of A, right? So what can you say about the columns of A if AX equals B has exactly one solution for every B in Rn?
They're linearly independent.
They're linearly independent, yeah. So V1 through Vn. Actually, you can say two things. By Goldilocks, you can say that the span is equal to Rn and they're linearly independent, which are the same thing. And again, all of these are equivalent to the row echelon form of A has n pivots. Okay, so all of these things are equivalent. And notice that, we have very different kinds of things in here, right? We have some very abstract kind of statements like this. Certain linear transformation is invertible, and we have very concrete statements like the row echelon form has pivots. And we have all kinds of things in between. And in fact, this gets even sort of a little bit wilder. Well, you now know, remember the Goldilocks theorem, right? So the Goldilocks theorem says that when you have n vectors in Rn, you have a lot of equivalences, right? So you have that being one-to-one and onto is the same thing as just being one-to-one. And is the same thing as just being onto. Having exactly one solution for every B is the same thing as having at most one solution for every B, and is also the same thing as having at least one solution. And being okay, these are spanning is the same as being linearly independent, right? So it's the same thing as saying V1 through Vn are linearly independent. This is the same thing as saying V1, the span is equal to Rn. And having n pivots is the same thing, which I mean, that's the bottom of all of these things. That's the same thing as having a pivot in every column, which is the same thing as saying it has a pivot in every row. Okay. So actually, all these things are equivalent, right? All these arrows are double arrows. Okay, so this is a kind of crazy looking theorem. Really, it's saying all these things are equivalent. And I mean, this is kind of, I think this slide is very important. So talking to a lot of people in office hours, it's sort of clear that each of these individual things is not very hard to show, right? They're all just kind of translations of concepts between the setting of linear systems, vectors, linear transformations. But really the power of this subject comes from the fact that all these things are very closely related. Okay, and this really comes together in the case of this invertible matrix theorem, where you have again, very important that this matrix is square. Okay, there's nothing like this for rectangular matrices. In other words, you need m equals n for this, right? So this is like a summary of all the different Goldilocks theorems that we've seen so far. Okay, so this is I guess what's called the invertible matrix theorem. And the point is that the statement of invertibility can be interpreted in so many different contexts, right? This is the context of linear transformations. This is the context of linear systems. This is the context of sets of vectors. And this is the context of looking at pivots. Okay. So there's a lot to digest here. Most of it is just a summary, but any questions about this?
Professor, I think this question is coming up a little bit in the chat. We're wondering if it's appropriate to use the if and only if symbols in like the blue cases because it's an n by n matrix, or is it not necessarily implied in some of these?
Yeah. All of these are only because it's n by n, right? I mean, all of these are because m equals n. So I mean, maybe you're asking, are these still true if m is not equal to n? No. Does that answer the question?
Yes, thank you.
So all of these equivalences are using that it's n by n. These are all Goldilocks equivalences, right? But remember, if m is not equal to n, it doesn't even make sense to talk about an inverse. Any other question? So now I'm going to briefly talk about how to compute the inverse, which is actually quite easy. So, well, what's the goal? So given some n by n matrix A, what's an inverse, right? Let's go back to the definition. So this is a good advice for this course. In general, when in doubt about what something means, just go read the definition. Well, it's a matrix C so that A times C is equal to identity. Okay, so my goal is given A, I want to find a matrix such that A times C equals identity if it exists. Right? Not every matrix is invertible. Because remember, invertibility is equivalent to all of these things, right? So, well, how would I do that? So, I mean, this is just an equation. A times C equals identity, right? It's just an equation. So, well, let C, which is an unknown matrix, think of it as a bunch of columns. Okay, so we want to find these columns C1 through Cn in Rn. So those are the unknowns. So there's a new kind of equation, right? It's like the whole matrix is an unknown. The whole matrix C is an unknown. Okay, but now what does this equation AC equals identity? So here what I'm doing is I'm zooming in, right? Initially, I think of C as being a square matrix. So C is also n by n, right? But now I want to think about it as being a bunch of columns. I can always do that, right? The zooming in, zooming out is really important. But now when I think about it this way, this equation star, let's rewrite star in terms of the columns, right? Well, what is it saying? It's saying that A times C1, A times C2, so the matrix with these columns. So I've just recalled the definition of matrix multiplication. That's the left-hand side, is equal to the identity. Now, what are the columns of the identity? Well, they're the standard basis vectors, right? Does anybody see how to solve for C1 through Cn now?
Can we write individual augmented matrices like AE1 to find C1?
Exactly. Exactly. That's a great idea. So this is just, you can just look at each column individually. And it's just a bunch of equations, right? AC1 equals E1, AC2 equals E2, all the way up to ACN equals EN. So it's n linear systems. And we know how to solve linear systems, right? Row reduction. So solve the following: A, E1, and okay. So now let's imagine that we're solving this, okay? So I mean, there are really two possibilities, right? One possibility is that the matrix actually is invertible. And if the matrix is invertible, what is the reduced row echelon form of A going to be?
Pivot in every column.
Pivot in every column. And in the reduced row echelon form, what do the pivots have to be?
Ones.
Ones. So actually, this has to look like this. And then on the right-hand side, what do you get if that's your reduced row echelon form? You actually just get the solution. Right. And but this matrix that's written here, I mean, this has a name. This is just the identity. So you get this if invertible. Because remember, if it's invertible, the reduced row echelon form is the identity. Otherwise, it's not invertible, right? So that's how you find the first column. And the important point here is that when you do the row reduction, if it's invertible, the reduced row echelon form. So by row reduction, I mean you finish it to get the RREF. That has to be the identity if it's invertible. Okay, but now I can do this again for the other columns, right? So I can do this for each column. A, E, N, row reduction, identity, CN. Okay. So I can solve N, I can do N row reductions. But there's actually something very special about these row reductions. So can anybody see what's special about these row reductions? Should I really have to do it N times?
Can't you just do it once?
Yeah, you can just do it once. Because the row operations only depend on A. If A is invertible, right? So if A is not invertible, then there's no inverse, right? And so really the conclusion is you have the same row operations in all of the above. So this is an observation. And so then there's a really slick way to do this, which is to do all of them in parallel. Do all row reduction in parallel. What that means is you make now a big augmented matrix with A and the identity. So now what happens if you stack E1, E2, E3, E4, all of them to be augmented columns, right? So what I mean by this is you have N augmented columns. And now you do one big row reduction to this thing. Sorry, that doesn't look very good. And if your matrix is invertible, you're going to get the identity here. And what are you going to get in the augmented columns? Can somebody tell me?
C? The inverse?
C, yeah, the inverse. Because in the first column, we're going to get the first column of the inverse. In the second column, we're going to get the second column of the inverse. So actually, you can find the inverse in just one row reduction, but you have to keep track of N augmented columns. Okay, that's the twist. Now, this is a fairly straightforward thing that if I do an example in front of you, it's not going to achieve very much. I'd rather focus on more conceptual things. So you'll do it on the homework. But if you have any conceptual questions about this, please ask.
So, Professor, when we row reduce the the augmented matrix, it cannot be there cannot be a free variable in it.
That's right. So if there is a free variable, or if for some reason you don't get the reduced row echelon form is identity, then it's not invertible.
Okay.
Okay,
So
so
it has to
maybe
be
I should
C.
add that case. So if RREF of A not equal to identity, then not invertible. That comes from the invertible matrix theorem, right? Invertible means the row echelon form has n pivots, which is the same thing, let's add it here, as the reduced row echelon form of A is equal to the identity. So if this doesn't work out, then okay, you figured out that there's no inverse. And if it does equal identity, then you just solved all these linear systems and you computed the inverse. Okay, so some people are getting confused about A inverse. So A inverse is the same thing as C, right? Yeah, so maybe I should emphasize that, right? We were trying to solve for C. Sorry, I should have just written C. So maybe I should write it like this. Let's write it as C. And that is equal to A inverse. Does that help? Because remember, a C satisfying these equations is what A inverse is. Yeah, so we're solving the system AC1 equals E1, AC2 equals E2, etc. But we're doing this trick to do them all in one row reduction. But now you have a big augmented matrix. Okay, so it is more work, right? It's not instead of one augmented column, there are n augmented columns. So this is the summary of how to compute the inverse. And rather than belabor it, you'll be doing a lot of this on the problems. But any questions about this?
So this procedure wouldn't work for any solution set, right? It would have to be the identity, like basis vectors.
So that's a good question. So yeah, so you're asking why can't you solve AX equals B for B1, B2, B3, etc. doing this, right?
Yeah.
Well, the reason is in this case, we've decided that if the reduced row echelon form is not identity, then we don't care, right? Now, in general, if you wanted to solve AX equals B1, AX equals B2, and all you cared was solving them, those may still have a valid solution if the reduced row echelon form of A is not the identity. So if you in general wanted to do this, the thing that goes wrong is this observation that in general the row operations might depend on B, right? In general for row reduction, because there might be a pivot in the last column or things like that. When computing the inverse, we have by definition we only care about the cases when A has n pivots. And that's why the row reduction cannot depend on the right-hand sides. And that's why you can do it in parallel.
Okay, thank you.
Yep. It's a great question. Any other?
I was wondering, like, writing this thing and as in the blue box, does it make the calculation actually simpler, or is it just a simpler way to write it?
It's a simpler way to write it. I mean, if you literally, it saves you the effort of writing the same thing down n times.
Okay,
So,
but I would still be doing the same calculation.
you'll still be doing the same calculation.
Okay, cool. Thank you.
Okay, so you're confused about in parallel. Okay, in parallel just means it's in quotes. It's not a mathematical term. It just means at the same time. Right? Instead of solving for the first column, then the second column, then the third column, just solve for all of them together. That's all I mean. Yep. Okay, so that's how to compute the inverse. So row reduction is, the gift that keeps on giving. Like it keeps, or as we're going to see in this course, you can use it to do all kinds of new things that it wasn't obvious initially it was designed to do. Okay, so now I'm going to talk about the determinant. Okay, the determinant is one of my favorite functions, but when I learned about it, I thought it was very mysterious. So I'm going to try to dispel some of that mystery, but first I have to show you the mysterious definition. But let's see, what's the motivation? The motivation for the determinant is you want a function that tests if a given square matrix is invertible. So what do I mean by this? Let's do a warm up. Let's consider a 2 by 2 matrix, right? With entries A, B, C, D. So how I want to define a function that checks whether this matrix is invertible. Well, A is invertible if and only if its columns are linearly independent. But for two vectors, it's pretty easy to check when two things are linearly independent, right? This is if and only if AC is a multiple of BD. Oh, sorry, not a multiple. Invertible is not a multiple, right? For two vectors. And how could this be a multiple of AC be a multiple of ED? Well, there are only two options. This if and only if A over C is not equal to B over D. That's one possibility, right? That's, I mean, that's what it means for two vectors in R2 to be parallel, that the ratio of the entries is the same. But this doesn't always work, right? So why is this not a correct if and only if?
Couldn't we have cases where we have like zeros? Oh,
Yeah, exactly. You have cases where you have zeros. So really it's or. So either A over C is not equal to B over D, or A and C are not both zero. Okay, right? Because if they're both zero, then again, it'll be linearly dependent. Sorry. So okay, I should clarify what not both zero means. I mean, or well, the negation of A equals C equals zero. Okay, so that so let's just write it that way. So, or that's not true. Anyway, this is just a fancy way of saying that AD minus BC is not zero, right? Because if A equals C equals zero, then AD minus BC is zero. And if one of them is not zero, then A over C not equal to B over D is the same as AD minus BC not equal to zero. So actually in the 2 by 2 case, we found a function, right? This. So we define determinant of A in the 2 by 2 case to be AD minus BC. And you have that the determinant is not zero if and only if A is not sorry, A is invertible. So that was maybe not maybe not such a big deal. It's a 2 by 2 matrix after all. Okay. So So now, well, I want to make one more remark. So what does this quantity mean? This quantity actually has a geometric meaning, which is important for intuitively thinking about this. So remark, the absolute value of det of A in this context is the volume of the parallelogram with sides given by the columns. Okay, so if I were to plot in R2, we won't prove this right now. If I were to draw the parallelogram and ask, given by the vectors that are the columns of this, so this, oops. So this region here, then that would be the absolute value of the determinant. Okay, so this is in R2, not in 3 dimensions. This is in R2. Okay, and that explains why this measures linear dependence and invertibility. Because remember, linear dependence means that they're parallel, which means that the parallelogram actually has no area, right? Sorry, I shouldn't say volume. I should say area, because it's in 2D. So that's what it is in 2 dimensions. It's a function. Yeah, sorry about volume. Let's call it area. It's a function that tests whether a matrix is invertible, but really it computes the area of this parallelogram whose sides are given by the columns of the matrix. Sorry about volume. So now our quest here in this lecture is going to be to generalize this to higher dimensions. But any questions about 2D? Why is A over C not equal to B over D? Well, remember, this means that they're not parallel, right? If you have 2 vectors in R2, parallel means that the coordinates are proportional. This is only for 2 by 2 matrices. We're going to do higher in a moment. Okay, let's now do n by n matrices. Okay, so given, so this is a definition. Given A n by n, say it has entries A11, A12, A13, A1n, A21, AN1, ANN. This is a square matrix. It looks rectangular, but it's square. Define. So this is a crazy definition, and I understand your. Don't expect to understand it the first time you see it. Define the determinant of A to be A11 times the determinant of A11. I'll say what that is in a moment. Minus A12 times the determinant of capital A sub 12 plus A13 times the determinant of capital A, A13, all the way up to -1 to the n plus 1, determinant of A1n. And what are these mysterious A12, capital A12, etc.? Let me say what they are. Where Aij is an n-1 by n-1 matrix obtained by deleting row I and column J of A. Okay. Now, I'm going to do an example very shortly. Let me just, again, clarify what's going on here. So this A11 entry is being multiplied by the determinant of the matrix you get after deleting the first row and column. So A1, capital A11 is going to be this matrix. And then you're going to do the same thing for A12, where you're going to delete now the first row and second column. And then for A13, you're going to have to delete the first row and third column. But the high level idea of this is that why is this a definition actually? This maybe this is the first time you're seeing a definition like this. Because it's not actually a formula, right? It's expressing a determinant of A in terms of determinant of some other matrices. So why is this a definition?
I mean, isn't it recursive? So eventually it'll just be led to a 2 by 2.
Exactly. So if you've done computer science, this is just recursion. Okay. This is a recursive definition, which is just a fancy way of saying is it expresses determinant of A in terms of determinant of smaller matrices. So if you repeat this, you'll eventually get to 2 by 2. So let's look at an example. So this is really, you can think of this as an algorithm, right? It's a recursive algorithm for computing it. So let's look at an example. Let's take A to be this matrix, 1, 2, 1, 0, 3, 1, minus 1, 0, minus 2. So what's the determinant of A? Well, determinant of A is going to be 1 times determinant of the minor, which is the matrix you get by deleting the first row and first column. So 1, 2, 1, 0, 3, 1, minus 1, 0, minus 2. But now importantly, you have to delete, right? So this is the first entry. And now I have to delete these. Okay. And then the rule says you flip the sign and go to the next entry. So minus 2 times determinant of, again, write the whole matrix. But now you delete the first row and second column. And then, okay, plus 1 times determinant of, again, 1, 2, 1. And this time you delete, sorry, I didn't mean to circle that. In order to be consistent, I meant to circle this, and you delete these. But now the point is those are all 2 by 2 determinants, right? So we can just compute this. So let's compute it. This is 1. So that 2 by 2 determinant is minus 6 minus 0, right? Minus 2. And here you have 0 plus 1. Because, right, you have 0 times minus 2 minus 1 times 1, which is 0 plus 1. And then you have plus 1. You have 0 plus 3. And here I've used the 2 by 2 formula, right? So what I'm really doing here This is a 2 by 2 determinant. And then, okay, this is -6, -2 plus 3, otherwise known as -5. Okay, so that's the algorithm for computing the determinant. It's a recursive algorithm. You'll have many more on the homework, and the best way to learn the algorithm is by doing. Okay. What I really want to dwell on in this lecture is why is this a good definition, right? So I should say this definition agrees with the 2 by 2 definition, right? So remark this agrees with the n equals 2 definition. If you were to do this procedure, if you treat the determinant of a number as itself and do this on the n equals 2 case, you'd get the same thing. So we've defined the determinant. Yeah, you keep finding subdeterminants until you get to 2 by 2, and then you compute the 2 by 2. Exactly. Now, this looks like a crazy function, right? The first time I saw this, I was like, how could somebody come up with this? This is a weird thing. So let me now tell you what the good properties of this are. Okay. Okay. And actually, I want to make one more remark. The remark is you can expand along the first column instead of the row if you want. Okay, we're going to use this remark in a moment. It's not obvious that that gives you the same thing, but it does. This is a really magical function. Okay, that's why it's one of my favorite functions. And just to be clear, it takes a square matrix and gives you a number. But let's now examine the good properties of the determinant. So any questions before that about the definition? Great question. Somebody asked, if you have a row or column of zeros, is the determinant 0? The answer is yes, right? I mean, if the first row is 0, you just get 0. And then, okay, you can actually expand along any row or column. But okay, let's just leave it at first for now. But indeed, as somebody asked in the chat, if you have a row of zeros or a column of zeros, the determinant is 0. Which, remember, it makes sense, right? We wanted this function to check if a matrix is invertible, and if a matrix has a column of zeros, it's not invertible. Okay, good question. People are asking what is a conceptual use. Let's get to that now. So to talk about the conceptual use, I'm gonna need to make one more definition, which will come up in the course. So a square matrix A is upper triangular if Aij is equal to 0 whenever I is bigger than j. Okay, this is what all this means is that there's some special entries in a matrix called the diagonal. And this is just saying you're 0 below the diagonal. It means if your row index is bigger than your column index, you're 0. And here you can be anything. This is called the diagonal. And the most important example is any matrix in row echelon form is upper triangular. Any questions about the definition of upper triangular? Okay, so now let's explore the good properties of the determinant. So good property number 1. And the good property is if is that a determinant of an upper triangular matrix is very easy to calculate. The good property is if A is upper triangular, so let's call the numbers on the diagonal lambda, is upper triangular. Then the determinant is really easy to calculate. It's just a product of the diagonal entries. Okay, why is that? Well, let's follow the definition, right? It's a recursive definition. Let's see what it does on an upper triangular matrix. Or let's just call it a reason. It's not even really a proof. Well, the reason is, I mean, let's just apply the rule, right? So det of A. So let's expand along the first column. Det of A is equal to lambda 1 times det of the matrix you get by deleting the first row and column, which is lambda 2 through lambda n. And notice that that's also upper triangular, right? Because the way I arrived at this matrix is by deleting the first row and column. But now, what are the other terms? I'm expanding along the first column, which just has a bunch of zeros. So you just have plus 0, plus 0, plus 0. Any questions about that step?
Professor, it's kind of a backward, but what does expanding mean?
Expanding means applying this recursive rule,
Okay.
right? So this I defined it for a row, but you can do the same thing along a column. So that was a remark here.
Okay. Got it.
And so I'm just doing that rule, right? So I have this entry times the submatrix you get by deleting that row and column. But then the key is all the other entries are 0.
Thank you.
Any other? Okay, but now I'm kind of happy, right? Because this is now, I can now apply the rule to this matrix, which is also upper triangular. And so now by the same reasoning, I get this is lambda 2, lambda 1, lambda 2 times the determinant of a yet smaller matrix. So every time I peel off one entry, I see all these new zeros. And if I repeat, I just get lambda 1, lambda 2, lambda 3, up to lambda n. Okay, so upper triangular matrices are great. As far as the determinant goes. And this reveals the first hint of why this is a good function. Right? Remember, we wanted to use this function to check if a matrix is invertible. What's going to happen if I apply this to a matrix in row echelon form, right? So consequence is if a matrix, let's call it R, n by n is in row echelon form, then if it has n pivots, that's the same thing as saying, so remember R is equal, has some entries lambda 1 through lambda n, 0 is below the diagonal. N pivots is the same thing as saying all of these are not 0. right? Because the pivots are going to be on the diagonal. On the other hand, if it has strictly less than n pivots, then one of those is going to be 0, right? Otherwise, you would have n pivots. Right? I mean, these diagonal entries, either if they're not pivots, they're 0 in row echelon form. A pivot is a leading non-zero entry. So if I combine this with this good property number 1, which I just want to emphasize is this, what do I get? Well, remember, invertibility means having n pivots, right? So the conclusion is R is invertible if and only if that R is not 0 for a matrix in row echelon form. So now we're beginning to see that maybe this function that we defined in this weird way actually has something to do with invertibility. Namely, it does the right thing for matrices in row echelon form. So that's good property number 1. Any questions about that?
Does this mean that to find a determinant, you can just put it in row echelon form?
It doesn't. You can do that, but this doesn't explain why, right? So we have to prove that doing row reduction doesn't change the determinant, and we'll do that next.
So can you only take determinant of n by n matrix, or can you take determinant of any size matrix?
No, it has to be square. Determinant is only defined for a square matrix, n by n. Very important. Determinant of a rectangular matrix doesn't make sense. Okay, so somebody already anticipated what I'm going to do next, which is now, again, I'm telling you, row reduction is really a magical algorithm. Like I'm shocked at how this algorithm can do so many things. Good property number 2 of the determinant is its behavior under row operations. Okay, so I'm just going to state this. I think this is the first thing in the course that we're not going to prove. I believe you can find a proof in the book. We're not going to prove it. But here's good property number 2. So let A be some n by n matrix, and let's do some row operation, just one, to get some matrix A prime. Okay. Now there are 3 possibilities for row operations, right? Well, the first one is you scale a row. So that means, let's say R1 gets some constant times R1. And you can ask, how are the determinants related? Right, so let's say I scale the first row of A to get A prime. Well, it turns out that the determinant of A prime also gets scaled. So if you scale one row of A by a constant C, the determinant also gets scaled. What's another row operation? Another row operation is you add a multiple of one row to another. So R1 gets R1 plus some constant times R2. And this is really kind of, I find this very magical. The determinant doesn't change at all. Okay, this is not obvious from the formula I showed you. It's not obvious, but it is. I mean, it's a really important sort of conceptual property of the determinant, which is why we care about that function. If you do this row operation, it doesn't change at all. And then finally, there's swap, which is you swap the role of row 1 and row 2. And here the determinant does change, but very little. You just pick up a minus sign. Okay, so that's good property number 2. We will not prove this, but you can read the book if you're curious. Okay, but now we can actually, again, use row reduction to compute the determinant. Right, so what's the upshot of this good? But any questions about the good property number 2? Okay, so the upshot of this, you can use a row reduction to compute the determinant of any matrix by reducing it to row echelon form, to REF, and that REF is now upper triangular. Okay, so for example, let's look at the same matrix again. 0, 3, 1, minus 1, 0, minus 2. And now, again, I'm going to do row reduction, right? My favorite algorithm that we've been doing throughout the course. And we just want to make it upper triangular, right? So remember, we have these 3 operations in our hand that we can do: scale, add, and swap. So let's start by just, I guess, adding to 0 out this minus 1. So R3 gets R3 plus R1. So this is an add operation. So you get 1, 2, 1, 0, 3, 1, 0, I guess 2 minus 1. And what's the change in the determinant? So this is my original A. And now I've done one row operation. What's the how does the determinant change according to this?
It doesn't.
It doesn't change at all. Okay. This is not yet in row echelon form. These are the pivots, but it's not yet. So I have to do one more row operation. Let's do R3 gets R3 minus 2/3 R2. This is again an add operation. How does the determinant change? Doesn't change. So you get 1, 2, 1, 0, 3, 1, 0, 0. Now you get minus 1, minus 2/3. So that's minus 5/3. And now this is in row echelon form, right? So this is my final matrix that I'm going to call R. And the determinant didn't change at all. So by good property 2, determinant A equals determinant R. And that's upper triangular. So by good property 1, that's just 1 times 3 times minus 5/3, which is minus 5, which is the same as I computed here. Okay, so I don't know. I find this very magical that there is a function like this. But what's the summary? The summary is you don't actually need to use that formula. You can just use row reduction again. So the summary is, let me just write it here. So if A is reduced to some R, which is in row echelon form, using only add and swap, which is always possible. You don't actually need to scale if you just want row echelon form. So this is an n by n matrix. Then determinant of A is equal to minus 1 to the number of swaps times determinant of R. And determinant of R is just the product of the diagonal entries. And that's it. Okay, so row reduction had this other hidden talent, which is that it also computes determinants. And that's in practice how you actually compute a determinant. Anyway, that's it for today. And I guess see you on Thursday.
Professor.
What does that? Oh, sorry.
Oh, yeah,
What does that little
ahead.
pi symbol mean?
Oh,
Like,
sorry. Pi means
if I-
product. Sorry. Okay, yeah. Let me not use that. Let me not use pi. This is R11, R22, or let me just write product of diagonals. Maybe that'll make it easier. Yeah. Any other question?
Professor, if we have, if we reduce it to row echelon form, don't we already know that A will have an inverse? So then what's the point of checking whether the determinant exists?
It's a great question. So the reason is later on, we're gonna be studying eigenvalues and eigenvectors, which is something we haven't talked about yet. And when you do that, it's gonna turn out you're gonna need a formula for checking whether a matrix is invertible, not an algorithm. And having the determinant available will allow us to use not this method, but this original method to get a formula for checking whether a matrix is invertible. So you're right. Later on, this is what we're going to use actually.
Okay.
But if you just want to check if a specific matrix is invertible, you're right. This method doesn't seem to add anything because if you do REF, then you kind of already get the pivots. So it's a very good observation. You're right.
Okay, thank you.
I want. Sorry, you go ahead.
Oh, thanks. So then in the second like bullet point you're talking about where you're talking about determinants, you said that A is invertible, and you concluded that it was invertible if A times D minus B times C is not equal to 0.
This was for 2x2 matrix, correct?
So then is that related to the consequence for property 1, where R is invertible if and only if the determinant of R is not equal to 0?
It's related, but here I mean, I didn't use that here. Here I just derived it from, the fact that a 2x2 matrix is invertible if and only if the columns are not parallel vectors.
Then how did you know that R is invertible if and only if the determinant of R is not 0?
That's a different reasoning. So that's this reasoning that R is upper triangular, right?
Yeah.
So let's think about a matrix in row echelon form, right? Either it has n pivots or it has less than n pivots, right?
Yeah.
Now, if it has n pivots, they actually have to be on the diagonal. That's the fact that I'm using. Right? If you have an n by n matrix with n pivots, they have to be on the diagonal because there's one in every column and one in every row.
Yeah.
But then these lambda 1 through lambda n, these numbers, those are the numbers on the diagonal. So if there are n pivots, then the product of the diagonal entries is not 0.
I think I get why if you have less than n pivots, it'll be 0, but I don't get how that's related to something being invertible.
Oh, well, that's because of the invertible matrix theorem. A matrix is invertible if and only if it has n pivots.
Oh, okay, thank you.
So you're right. I'm using this like heavy theorem that we stated earlier.
Mm-hmm.
And in fact, I might as well add to this now that the lecture is over. This is if and only if the determinant of A is not 0. Uh,
So
yeah.
for the row operation swapping, like, does that matter? Like if I swap row 1 with row 2 or row 1 with row 3?
Anything, any swap will flip the sign of the determinant.
Okay. Thank you.
So if you do even if you do an addition where one of the rows has to be multiplied by a scalar, that doesn't count as multiplying it by a scalar. It's just considered an addition.
Yeah, that's different, right? So adding a multiple of a row is not the same thing as scaling a row, and they have very different effects on the determinant.
Okay.
Scaling a row actually multiplies the determinant by a number.
Right.
Professor, could you explain again why why we can't use the invertible, like AI augmented matrix for AX equals B?
Sure. So, well, you mean by for B1, B2, Bn, and so on, right?
Yeah.
Okay, so this is a separate question. So let me